Okay, so we've seen a few examples of projectile motion and motion in 2 dimensions. And what we're going to do in this lesson is we're going to do a couple more examples that are a little bit more challenging and kind of continue to work on this method of breaking up our 2-dimensional problems into 2 one-dimensional parts. Okay, so we're gonna treat the horizontals separate from the verticals, and then to recombine everything at the end and get an answer. Okay, so what this all implies is that we handle x components and y components separately. So if you have an initial velocity in the x direction, that cannot show up in any equation in the vertical equations that you're going to put together. Okay, each set of equations, vertical and horizontal, are going to have their own givens, their own unknowns, and their own equations. Okay, I'm going to use the guess method to evaluate the problems. Right, it's going to keep my solutions organized for you. You don't need to use this method, but it's suggested, especially at the grade 11 level where we're just learning to do kind of really big problems like this. So here's the first example. A circus performer is to be shot out of a horizontal cannon at 40 meters per second at the top of a cliff 100 meters above the ground. How far from the base of the cliff will he travel? This question that we're about to do is exactly the same as the second example that we did in the previous lesson. Okay, it's like the arrow that's being shot horizontally from a position that's higher than where it ends. Okay, so let's take a look at what our little diagram looks like. We're going to set the 0 point as being where the cannon is, so the top of the cliff. And very often you'll see that done when people choose their coordinate axes. They'll set the 0 point, the origin, as where the motion begins. Of course, because we have these sign conventions, we can put 0 wherever we want. But in this example, I'm going to put 0, 0, 0, right where the motion begins. So as soon as the circus performer leaves the cannon, that is 0. Which means that where he falls to in the y direction, you can see there, is going to be minus 100 meters. Because it's lower than where he started. So of course that means it has to be negative with our sign convention. So that's what we've got. What do we know? Let's list our givens. So here's what we know. We know the initial velocity in the horizontal direction, and it's 40 meters per second. Because it's a horizontal cannon, we also know the initial velocity in the y direction, and it's 0. For projectiles, the acceleration in the x direction is 0, always, and the acceleration in the y direction is due to gravity, and it's minus 9.8 meters per second squared. What do we know about displacements? Well, the displacement in x is what we're trying to find, because we're trying to find how far in the x direction from the base of the cliff will the circus performer land. But we do know the displacement in y, because we're talking about, of course, him landing, so it means he's eventually going to hit the ground. And so that's 100 meters below where we started. So our displacement in y is minus 100. So let's take a look at our horizontal equations first. And what we can say is, okay, well, we know that the acceleration in x is just 0. So this right here is really equation number 3, v1t plus 1/2 at squared, but I haven't written the plus 1/2 at squared term because the acceleration is 0, so that term cancels out. So let's sub in what we have. Well, dx is actually what we're looking for, but we do have v1x. We don't have time. We need to find it from somewhere. We need to find out how long it's going to take this guy to hit the ground. And of course, now at this point we say, okay, well, are we stuck? Because we have one equation and we have 2 unknowns. And of course, what you should be saying is, no, we're not stuck. Of course we're not stuck, because what's the only variable that can show up in the x and it can show up in the y? is time. So let's go and look at the vertical direction, because this is where we're going to find time. And what we have is, here's equation number 3. Okay, the same thing, but we've written it with y subscripts so that we can differentiate. Okay, it's a different equation because it's talking about a different direction. And let's sub in what we know. Well, we know that dy is minus 100. v1y is 0. ay is minus 9.8. And so all of a sudden, hey, here we go. We get one of these really nice simple quadratics. We can rearrange and take the square root. And we come up with, of course, t is equal to plus or minus 4.5 seconds. And what we should ask is, okay, do we need the negative root? In general, we're talking about time, so no, we actually don't need the negative root. It's inadmissible. Okay, so let's push the page up, continue the solution. We now are back to the horizontal. So we've found time, so we're going to flip back to the horizontal, and we can say, oh yeah, the initial velocity in x was 40 meters per second. The time it takes him to hit the ground is 4.5 seconds. And so we can solve and we say 180 meters. And we can finish this one off by saying, okay, well, his range, how far he travels in the x direction, is 180 meters from the base of the cliff. So that's kind of the standard straightforward example. But of course, we can do lots of other things with projectiles too. So here's another question that we're going to do. But now, the cannonball is shot out of the cannon. Yes, it's got a horizontal velocity, but it's also got a vertical velocity. Right? So now it's shot in an angle. And if the cannon's sitting on top of a cliff that's 100 meters high, so almost exactly the same, find the range of the cannonball and find the maximum height. So let's redraw the diagram because it looks a little bit different. Now instead of just shooting horizontally, the cannon's kind of pointed upwards a little bit. Right? So it's at an angle to the horizontal. And the first thing is that, okay, well now we know the initial velocity in the x direction, but we also know the initial velocity in the y direction. So the range, finding the range is very similar to example number 1. There's just one small little difference. Here's the horizontal direction, and this is what we know in the horizontal direction. Okay? Here's what we know in the vertical direction. And you'll notice that the only difference here is this v1y is now not equal to 0 because the cannon wasn't launched horizontally. It was launched horizontally and vertically. So we have this 20 meters per second. Everything else is almost exactly the same. So now we say, all right, well, let's go through and look at our equations. In the horizontal direction, this is what we have. And of course, ax is still equal to 0. So really, we have almost the identical equation in the horizontal direction. Vertically, though, now we have something a little different. v1yt plus 1/2 ayt squared. And before, remember v1yt was 0, and so it canceled out that term. Well, we don't have that anymore, and herein lies the difference. Now we have 4.9t squared minus 20t minus 100 equals 0. So this has all been moved over to the one side, and of course this has the form of a quadratic equation. And we can solve the quadratic equation using our formula, b plus or minus the square root of b squared minus 4ac all divided by 2a. And of course that's the quadratic formula, and of course if you need to remember the quadratic formula, you may have to go and review that, but really that's all it is. It's finding the roots of any quadratic equation. And what we find is, of course, this is going to give us 2 roots. We can continue to simplify, and we find, okay, well, t is either 7 seconds or t is minus 2.9 seconds. Again, the time in this case is inadmissible, so we don't need to find it. So what are we going to use? Well, we're going to use 7 seconds, and we're going to take that and go back and solve in the horizontal direction. 40 meters per second was the initial horizontal velocity times 7 seconds, and of course we get 280 meters. So the range here is 280 meters. And that's part A. So almost exactly the same. However, we're also asked part B. Find the cannonball's maximum height. And so there's something that we need to ask ourselves, is that at the maximum height, like what happens to the ball at the maximum height? So really to any projectile at its maximum height. So if you take a ball and you throw it right up in the air and it goes up to its max height and then comes down, what is the velocity of the ball in the vertical direction at its max height? And of course, we've done a couple of problems like this. And so you may have said, oh, well, at the max height, the velocity of the ball is always 0 in the y direction. It may still have a horizontal velocity, but its vertical velocity goes to 0. So at its max height, Vy is equal to 0. And so we say, oh, okay, well now, what do we know? Well, we know V1y, because we've already solved for that. We know Ay. We want to know what dy is, because that's our displacement in the y direction. So that finally, our second velocity will give us 0. And the reason that we want to say this is we want to say, oh, well, what's the distance it takes for this object to travel up to a second velocity of 0? So basically, what's the distance between where it starts and where it gets to? And so this is equation number 5, which is a very handy equation to use in this case, because we have V1, we've got V2, we've got A, and we're looking to find D. And so when we sub everything in, we've got an initial velocity of 20, got a final velocity of 0, we've got an acceleration of negative 9.8, and so we can put all this together, and what we find is that dy is equal to 20.4 meters. And we say, okay, 20.4 meters, where is that in relationship to? Well, it's in relationship to where the ball started its motion. So we say then that the max height is 20.4 meters above the cliff. Of course, how high is this above the ground? Well, it will be 20.4 meters plus 100 meters, because the cliff is 100 meters above the ground. So it's always important in your final statement to say, okay, well, what's it measured in relation to? So that's another question that's very typical in projectile motion stuff is, hey, what's the max height of the projectile? Final example is a little bit different yet again. A golf ball is hit with an initial velocity of 30 meters per second at an incline of 50 degrees. So here I'm not telling you what the x component of the initial velocity is and what the y component of the initial velocity is. I'm actually telling you what's the initial velocity vector, and we're going to have to resolve that into its x and y components. But I tell you that the ball lands 2.0 meters above the point of impact and then 70 meters away. So what's the final velocity of the golf ball? So I'm asking you for some different stuff here. And let's draw our diagram first. Here's the golf ball. It starts out. It lands 70 meters away from and 2 meters above its point of impact. Okay, so let's start working on what we know. Here's dy, our change in the y displacement. d2 minus d1. If we say it starts at 0, we put 0 where the motion begins. 2 minus 0 is just 2. So its change in its displacement in the y direction is 2 meters. Of course, its displacement in x is 70 meters because it starts off at 0. It ends 70 meters away. It impacts the ground 70 meters away. So dx is equal to 70. Okay, what about accelerations? Well, it's a projectile, so we know the acceleration due to gravity is negative 9.8. And after it's been hit by that golf club and it leaves and it becomes a projectile, its acceleration in the x direction is 0. Okay, so we've done that. We want to know, so we've talked about displacements, we've talked about accelerations. We want to know velocities though. And so what's going to help us find that final velocity? Well, let's talk about an initial velocity, because we do know what those initial velocities are. So let's draw a vector diagram of the initial velocity. So here's our v1, it's equal to 30. We know it's at an incline of 50 degrees, and there's our two components, v1x and v1y. Can we find v1x and v1y? Absolutely. Let's use trig ratios. Okay. We know that the sine of 50 degrees would be equal to the opposite over the hypotenuse. So v1y divided by 30. And we can solve that, and we can say, oh, v1y, if we rearrange, is 30 sine 50. And if we do that, punch that in our calculator, we get 23 meters per second. What about v1x? Well, v1x is the adjacent side. So the cosine of 50 is equal to the adjacent over the hypotenuse. And once again, we can rearrange and punch this into our calculator. And we get 19.3 meters per second. So look at all the information that we've extracted from this question. There's tons and tons of information in here. Okay. Now, let's start setting up our equations. In the horizontal direction, what's the final horizontal velocity of the ball? It's a projectile. You should be saying that v2x equals v1x, which equals 19.3 meters per second. Because the ball does not accelerate or change speed in the x direction. It has a constant velocity. So our work is done for us. What about in the vertical direction though? Because we know that this is going to change. So let's actually take a little bit more room here. Here's the vertical direction. And what we have is, well, we have v1, we have accelerations, and we have displacements. So we're going to use equation number 5 again, because it's probably the most useful equation to use in this case. v2y squared, which is what we're trying to find, equals v1y squared plus 2ay dy. And when we sub these numbers in, okay, we get a number like this that we can solve for, and we get v2y equals plus or minus 22.1 meters per second. Now, again, we get the plus or minus because we took the square root. And we're very, very used to throwing out the negative root as being inadmissible. Okay? There's two answers here, right? So plus 22.1 meters per second minus 22.1 meters per second. But let's not just throw them away, because we're not talking about a time anymore. If this was a time and we got plus or minus like 22.1 seconds, then I'd say, yeah, throw out the negative root. But let's be careful. The ball actually, if you look at the diagram, is at 2 meters at 2 different times. It's at 2 meters when it's going up and you've just hit it, and it's also at 2 meters on its way down when it hits the ground. And if we want to look at a little diagram of this, here's our original little diagram. Take a look at this 2 meter point and extrapolate across. Yeah, the ball's at 2 meters when it hits the ground. We can see that. That's the end point. That's what we're looking to solve. But the ball's also at 2 meters at the very beginning. 2 meters at the very beginning, though, the velocity at that point is upwards. The vertical velocity is in the upwards direction because it was hit up in the upwards direction. So that's the positive root. The answer that we want is actually the negative root, the negative 22.1 meters per second, because that's reporting when the ball's on its way down. So we don't want to just throw it away. Here's what our vector diagram looks like. We got 19.3 meters per second in x and 22.1 meters per second in the downward direction in y. So we'll use the Pythagorean Theorem to solve for the overall final vector, 29 meters per second. And we'll solve for the angle, and of course it's just the inverse tan of 22.1 over 19.3, which is 49 degrees. And so we can report the final velocity as 29 meters per second right, 49 degrees down. You could also have said east, 49 degrees south, and that would have been just fine. And that's it. That's projectile motion.